Welcome to another broadcast from mindyourhealthcast.com. Now, if you recall, or happen to have watched our last broadcast, you'll remember that this was the third idea that I had made mention of, that there were three great, I wouldn't say discoveries, but three great awarenesses that I learned in my life that have had a tremendous influence on the way I work and the way I view the world and myself, etc. And so this was number 3, which was quantum physics. And this is probably the most difficult one of all the three to not only communicate but to understand. It's something that you're not going to pick up a small article and read an overview and say, oh yeah, I understand quantum physics. It's much more complex than that, and yet it's simple in principle, like so many great things, simple in principle, difficult in comprehension and application. And what it appears is, of course, that in our world, we have had a view of what the world is and what reality is that goes back for a long time. And once quantum physics came along, there began to be a differentiation between what was called the classical view and the new quantum view. And you know, the word quantum, as I mentioned, gets abused and misused tremendously, but we'll get back to that in a minute. But the classical view is the way that everything has been operating in terms of science and everyday life and our view of ourselves and our view of the world, which came out of, ultimately, Newton and his laws of mechanics and physics. And basically it came down to thinking that the world is like a clock and everything is like a clock, and it runs according to fixed principles or laws, and that once we know the mathematical principle or law, we can calculate into the future and say this is what's going to happen next month, the next year, 10 years from now, and we can move backward and say, well, 35 or 50 or 500 years ago, such and such was true because this seemed to be the fixed laws of everything. And so with that idea in mind, everybody thought it was solved. And as I mentioned, at the turn of the century into the 20th century, the 1900s, physicists felt that everything really had been discovered about physics, and that it was probably a waste for young men to, or young women as the case might be, to get into the realm of physics, because we already understood it except for a couple of small items that we hadn't quite explained yet. Otherwise, we had really come to an understanding of how everything works. And it seemed pretty reasonable at the time, I guess. But then Albert Einstein comes along, and some of his ideas and concepts and theories throw a wrench in the gears a bit. In fact, more so than Einstein would have wanted, and as it ended up, he spent a lot of his life having pulled away from mainstream physics in a sense, and was working on some type of a unified field theory of everything. Up until he died. But he was very unhappy with some of the things that had become unleashed as a result of some of the ideas that he came up with. In fact, got a Nobel Prize for. And that had to do with the photoelectric effect. I know everybody thinks of him in terms of relativity and his famous E equals mc squared formula, which was a revolution in thinking at the time. However, it's interesting that he did not get a Nobel Prize for that. He got a Nobel Prize for a paper he wrote on the photoelectric effect, which is why a beam of light, which at that point was considered a wave, because in those days waves were quite clear and distinctly different than particles or matter. And so we knew that certain things were matter and certain things were waves, and there was the mathematics for waves that had been developed by scientists by the name of Maxwell, and there was a series of principles. Everything else had to do with particles and how particles built into larger pieces of material and how they behaved. And so it, as I say, was pretty well solved. But here he comes along, and one of those loose ends had to do with this photoelectric effect. Why would a wave, a beam of light, a wave, knock electrons out of place on a piece of metal if in fact they were a wave? But yet it was known that this was true. In fact, when I was young, there was the early days of electronics where you still had vacuum tubes, but you also had a special tube called a photoelectric tube that had to do with this idea that when a beam of light hit it, it would knock electrons off of this plate inside this tube, and so you could make it act as a switch. So if you had a beam of light and somebody walked through that beam and broke it, it would alter that movement of electrons and trigger a switch that would open or close the door and so forth. So that became a practical application of the concept of the photoelectric effect. But it was a contradiction in physics because it was a wave. So how was this wave of light acting on this particle, which was an electron? And so it didn't make any difference if they didn't quite understand it. They knew it worked, and so as happens so many times, once a new principle is uncovered, pretty fast that people come along to make some type of practical application. So I had one of those. Electronics was an interest of mine from as far back as I can recall, and so I had obtained a photoelectric tube, and it was interesting having it turn on and off things. Of course, now in some of the newer realms, we can turn things on and off with our mind, but we're not going to go there yet. But it was interesting, and I enjoyed the whole idea of electronics. I built my first crystal set when I was probably about somewhere between 8 and 10, maybe 10, and was able to listen to the radio without any batteries, without any vacuum tubes, just by using this circuit that it utilized a crystal that acted as a diode or a detector, and you could put up an antenna and run the signal into a tuner, which could be a coil of wire with a movable arm that changed the number of wires that were in the circuit, which means it acted like a oscillator, resonator, and then you could put on headphones and you could hear radio programs and so forth without any electricity, and it could work any place. You didn't have to worry about batteries, etc. So then I went on to learn about vacuum tubes and how they worked, and on to the whole realm, and eventually to transistors and solid-state electronics, and then eventually into IC chips, and it just went on and on. Now, of course, it's become tremendously miniaturized and tremendously sophisticated, and can do all kinds of things with very small amounts of electricity movement compared to some of the old big units that required huge amounts of voltage and amperage to run. So anyhow, that was the way it was, and here Einstein starts this discourse into how can a beam of light, of electromagnetic waves, knock out solid material. And out of that, another physicist, mathematician comes along, and he calculated some mathematics about waves and wave function, and eventually it got to the point that it became evident, without going into great detail, it became evident that actually light was strange, because under certain circumstances it could act like a wave when it moved through space, And at other times it could act like a particle and knock off electrons out of other atoms or molecules. And so that was a kind of a queasy feeling in the stomach of Einstein, because even though what he did explained what happened, he didn't like the implications of it. And pretty fast, a lot of other things happened. Some scientists came along and said, well, if a beam of light can in certain circumstances behave like a particle, then possibly particles under certain circumstances can behave like a wave, such as electrons, because at that point it had already been decided that an atom was like a miniature solar system. You had a nucleus, which is like the sun, and you had electrons moving around that nucleus, which were like planets. And so basically it was very consistent with our worldview of a mechanical universe, a clockwork universe, and so no matter how far down, it looks like it was the same thing. In fact, when I was in school, I originally was taught that the atom was the smallest unit you could break matter down into. And that were the basic elements, you know, the table of the atomic elements, which were, if I recall, 92 originally when I learned about math and physics and chemistry and so forth. But as time went on, of course, they discovered more elements and they created some more of them artificially, and so the atomic table went to over 100 items. But as I say, when I was young, I was taught that it was the smallest unit that it could be broken down into. Was an atom. Well, then later, as time went on, we got into subatomic particles, meaning you could separate electrons and protons, but then it came a time when we went a step further and said, now wait a minute, we can break the protons and neutrons down even into more basic material called quarks, and that opened up a whole new ball game. So it seemed that no matter how far down you went in the scale, there was something beyond that. And that was a big eye-opener to a lot of scientists, that you could go beyond the subatomic particles, the protons and neutrons. And of course, out of this whole thing with the quantum side, a whole new thing came out of the electron. At some point, it was discovered that electrons really don't exist as particles at all. They exist as a wave of probability, and the only time they become a particle is when you look at them and set up an experiment to see them as a particle, then they behave as a particle. But if you set up an experiment that looks at them as a wave, they behave as a wave. And of course, this kind of really threw a wrench in the gears. Now, how can an electron not exist, and why would it only exist when you look for it to exist, and why would it only exist because you look for it as a particle? And so there's a famous double slit experiment. We're not even going to get into that at this point, other than to say, if you want to learn more about it and read into quantum physics, I've mentioned some of the books before, and you probably might want to look into it further. But don't be surprised if this becomes a long-term project to, bit by bit, comprehend what this is all about. What happened is that it became very obvious at a certain point in physics that on the subatomic scale, or even down at the atom scale, things operated differently than they did on the macro, meaning our everyday life scale. And of course now I have questions about that. I'm not so sure that chaos theory does not explain quantum effect in our real, quote, regular everyday world. And we may talk about that. I'm sure it looks like that this is probably going to be at least 3 sessions, but I'm giving you some different perspectives about this, because once you jump into it, it's going to be fun to make sense of it for a little while. Why do I talk about it? Because it's extremely important, because if you want to understand how the world is and how it works, and why seeming contradictions aren't really contradictions if you have a deeper understanding, and how it applies to things like health and illness and thinking and emotions and problems and et cetera, et cetera. In other words, the scope is extensive as far as what it really involves. It's easy for us to set it aside and kind of ignore it and just think in everyday terms of what we've always thought, that matters matter and waves are waves, and neither the twain shall merge, except maybe one affecting the other. So at any rate, I mentioned last time you should be viewing a movie called What the Bleep Down the Rabbit Hole if you haven't. It's going to give you a bit of a feel of the application in life of some of the principles that we're talking about and how it affects us in our life. Now the movie is about a short period of time in a lady's life, a young lady who's a professional photographer, and some things that happened to her. And at different points, they go to some scientists, such as William Tiller, who I mentioned his books would be very important for you to understand and read, and Fred Alan Wolf, which I mentioned already, his material. But there's several others in there that talk about either from the mind consciousness application or from the world as we think we know it application. These people have written a lot. I'd say Wolf, of course, has written a long string of books. I mentioned in particular Taking the Quantum Leap as an introduction to the whole way of thinking about quantum. And you know, it's funny because it's become a common term in our society, as I've mentioned before. We talk about taking a quantum jump, and of course in most cases, well, I guess some people kind of have an idea of what they mean by that. But what it really means is the term came from quantum physics, but it had to do basically with electron action and the idea that electrons are in an orbit when we view them as particles around a nucleus, but they can jump from this orbit to this orbit without ever being anywhere in between. And it's like they're here, they're here, they're here, but they're not moving to that orbit. They're disappear here and appear here instantaneously. And that was referred to as a quantum jump because Planck's constant became a mathematical constant that would predict that that's what would happen at that ratio. Now, the reason things stay where they are, in my mind, have to do with something called resonances. So why is the first orbital around the nucleus of an atom contain, when you look, a maximum of 2 electrons? But the fact is that before you look, there are no electrons, but there is a dual wave of probability that says if you do look, you're going to find the electron here or here. You'll never find more than 2 in that first orbital. And you may only find 1. For example, hydrogen only has 1 electron in the orbital, so it has an open spot. So what happens? Hydrogen is open to combine with other materials that can share electrons to close those, because there's a thing about nature and closure. Things like to be closed. And so before that happens, the hydrogen atom is always, even though electrically it's balanced with 1 proton and 1 electron, it has activity-wise the capability of doing something more because there's only 1 atom in that orbital. But it's, 1 electron, but it's really not an electron. It's a probability wave that can be an electron if you look for it. And that means if you set up an experiment to find the electron, if there's only 1 there, then 50% of the time you'll find it in one of the 2 locations it could be, and the other 50% of the time you'll find it in the other location that it could be. And but we never can predict where it is at any given time, only the likelihood of where it could be, and we only can know for a fact when we look. And when we look, in quantum physics is called collapsing the wave function. That means that this wave of probability collapses and becomes, in appearance, an electron or matter. But then when you quit looking, it immediately is no longer a solid electron. It is now a wave of probability of electron. I'm just throwing this in bit by bit to kind of stretch the neurons in the brain a bit, and mind. Now then, we haven't talked about the mind part yet, but we will be talking about it, and this has influence on everything once you begin to see how it works. Or I shouldn't say see how it works, get a feeling for the principles of what we know about it so far. Now, there's a certain basic set of, and I threw this in because I'm wanting you to start thinking, now wait a minute here. This is getting a little bit confusing, and as I say, it's not easy to communicate, and you know, I've wrestled with it for a long time, and I would say at best I only have a fair understanding, and I'll have to mention again that Niels Bohr from Copenhagen, Denmark, who was one of the big players in the early days of quantum physics as it first was coming to the foreground, and physicists were beginning to shake their head and saying, wait a minute, what's going on here? I thought we knew all about the universe and we knew how it worked. So Niels Bohr was one who made the comment, if anyone reads the definition of quantum physics or quantum concepts and doesn't think that it's totally outlandish, they did not understand what they read. Because it is... We're talking about probabilities, and with probabilities you have uncertainty, and when you have uncertainty, then you can't pin something down absolute. See, we've always liked the thing of the Newtonian concept is that we can pin it down absolutely. But wow, the quantum physics says, now wait a minute, the universe doesn't work like that. It works on the idea of probabilities. So here we have a quantum wave of possibility, and the more amplitude the wave gets, the more energy there is for it to do something, and the more likely it can collapse into what we consider to be a particle or something we can see, touch, feel, run experiments on, and etc. Okay, so we got to throw into some of the basic ideas so that you can begin to wrestle, and we'll talk about the books again. And as I say, we'll talk a little bit about the application to health and disease, etc. First of all, we were talking now, what I've just been telling you, it has to do with discreteness, about the energy existing in certain packets or waves. And it seems that there's a ratio in nature called the phi ratio compared to the p ratio, which everybody refers to as pi. You know, the 3.1416 pi, when you're doing mathematics involving circles or spheres, you get into the radius and the pi factor, which is a constant. Okay, well there's another constant that's kind of like pi called, but pi in Greek it really is phi, or p, not pi. So it's P and phi. And phi is another ratio in nature, that it seems that things arrange themselves in nature in accordance with a sequence of resonances, which were, a formula for it was developed many, many years ago by an Italian mathematician by the name of Fibonacci. And Fibonacci realized that there is a progression in nature, but it's not like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It ends up being 1, 2, 3, 5, 8, 13, 21, 34, 55. It goes a different sequence. And that this sequence, each of those are like resonances. That means that it's a stable vibrational point. And so we have in quantum physics this discreteness idea that the electron is either in the first orbital, or it's in the second orbital, or it's in the third orbital. And those are resonances that it can stay in that orbit. But what we cannot tell you in advance is where that is going to be in that orbital. And we can set up experiments to look, and we can get evidence that while we're looking, we see it here, but we're going to get into another principle called the Heisenberg uncertainty principle that's going to rattle the chains a little bit more. But anyhow, there is these series of resonances. Now, I found that out in homeopathy, that the same thing is true. And in dilutions, there are certain dilutions that are more powerful, that really have a strong effect over others, and for a particular person at a particular time for a particular problem. And so, you know, we talk about the 6x scale, which is like a 1/10, actually 1/9, 1/10, because it's 9 to 1, 1/10 of dilution being a 1x. Okay, so that's a resonance. And it can do certain things, but other things it's not as powerful. But as you add energy to it and raise it by diluting it, you raise the energy, then you get to a 3x is becoming more powerful. And the common one has been 6x, but I believe 5x, which is the next in the Fibonacci sequence, is extremely powerful. And then you move right on up the ladder. So the next one would be 8. Now 8 is not very commonly used, although occasionally I've run into it in 8C as well as 6x, and I mean 8x. So the 8 is one of those numbers, but then it jumps to 13. Now 12x is used a lot in homeopathic medicine, but really 13x is more on that resonance level, which means it's going to have a very strong energetic impact at resonating with things because of the fact that it is the way nature works. Okay, so there is this discreteness that at certain resonances, then things are able to be detected and they have strong effect. The second big principle of quantum physics that we need to consider is the wave-particle duality idea. As I mentioned, what it was found ultimately, again, depending on how you look, because the observer, the person setting up the experiment, in a great way affects the outcome of the experiment. So much for objectivity. That's why you have one person run an experiment and it comes out a certain way, another person runs the same experiment and it comes out differently. And the second one says, well, the first one must have messed up someplace. And of course, the first one's going to say, no, I didn't. The second guy messed up somewhere because this was very tightly controlled and this is the way it came out. But the person being part of the experiment affects the outcome, which explains a lot of things. Something we talk about in everyday life, you get what you expect to get. It does have an effect because consciousness is a big factor in the whole realm of everything, and hopefully when we go to the next broadcast we can kind of deal with this consciousness, because I'd say that's the big thing that means the most to the average person, is how this affects you on the mind consciousness level and what the implications of that are, both in health and sickness and in your life in general. So we'll work on making that application. But in the meantime, if you get a chance, there's some good books by Roger Penrose, who is a physicist, mathematician, scientist at Cambridge, and he was the doctoral advisor for Stephen Hawking, which you may or may not have heard of, who is the considered to be the most intelligent, deepest thinking person since Einstein, who unfortunately, here you had Einstein, who was robust to health-wise, did pretty good in his life, and then you have Stephen Hawking, who has amyotrophic lateral sclerosis, should have been dead years ago. In fact, he had the first symptoms when he just had started his doctoral program at Cambridge. And so here you have him, who he deteriorated physically so bad that he can only move his index and thumb a little bit to depress a switch that can activate a computer, which can type out words and create sentences and feed it into a voice synthesizer that can speak for him. He's extremely brilliant also, and so he was under Roger Penrose. So Roger Penrose and he became good friends and have had all kind of interesting little controversies about different theories, and it's been kind of humorous the way they've carried it on over a period of time. But anyhow, Penrose has written several books. Stephen Hawking has too. And I say that these would be good books for you to read if you're really interested in life, the universe, how things work. Very good books. A couple of Penrose's I think is very good. It's called The Emperor's New Mind, and if anybody remembers the story of the Emperor's New Clothes, then this is kind of a takeoff on that. And then the other one is called Shadows of the Mind, which is very good. And in recent years, Penrose has joined together with another great thinker in this country out of Arizona. His name is Hemroff, and anyhow, Stuart Hemroff. And the two of them have written a lot of material together on the nature of consciousness and the brain and memory and all that. So it would be good to get into that. And then they have a new one on the universe that the two of them have written jointly. If you go to Amazon, you can find it. And those will give you some information to kind of get going in all this. So this duality of particles is very important because bottom line it is that under certain conditions something behaves like a particle, and other instances it behaves like a wave. And the way you set up the experiment will demonstrate it to be either a wave or a particle. Now if you read any of the books on quantum physics, then you'll see, and I'm sure that Fred Alan Wolf in his introduction to quantum physics called Taking the Quantum Leap discusses what's called the dual split experiment that showed that when an electron goes through a plate that has one or two slits in it to a target screen, that if that single particle encounters a plate with only one slit open, it goes through as a particle. But if you have two slits, if it going through as a particle, it seems to turn into a wave and go through both slits at the same time and create a wave pattern on the target instead of a particle dot where it would have made a single spot if it were a particle. And so that's called the wave-particle duality. And again, as I say, we're stretching your brain, and hopefully you'll be able to find some practical application out of all of this by the time we're done, and at least get you started thinking in a whole different way. It would appear to me that our time is up without making this too long, because I know we already are stretching. I can hear creakiness in a lot of people's cranium already. And we'll get back to it next broadcast. And I think what we're going to do is, I say, we want to make some application, because the whole idea of bringing this up was to say, well, yeah, it does have an application in the world, and here's how it applies. So the next time, we're going to finish a few of the peculiarities, which there's not a big long set of them. There's a few basic principles, and once you kind of grasp these, at least it allows you to work with the quantum concept, even though, who knows, I mean, if anybody has the right in-depth understanding, but at least every test or experiment that's ever been set up to test quantum principles has proven to be true and accurate. That's what I will say. So there's evidently something to it, because it holds consistent that every kind of experiment you set up says, yep, it's true. It works that way. So until next time, we want you to jump in, see the movie What the Bleep Down the Rabbit Hole. If you haven't seen it yet, that'll give you some visuals and introduce you to a few of the players that have written a lot of material about it. And the next time, we'll go into more depth. It was nice being with you again, and until the next time, be healthy.